Hey everyone, Big Meg here. Welcome to another QualQuest video. I told you that I was going to try and do some hard problems, but this last test just totally kicked my butt. So, as a way to relieve myself, I'm just going to do three of the problems from the easier part of the test, as a way to compensate. So here's number one. We have a nonlinear equation where we want to solve for y, but it's also in terms of y. Oops, there we go. Now it's in order, okay? So, how do we solve for this? Alright, so in solving this, we make one obvious notice. We pay attention to one obvious thing at the beginning. When we integrate y squared as a function of c, and then we integrate with respect to z, that's going to be a constant, because we've gotten rid of all our variables and we're evaluating between 0 and 1. So let's just call that a. So then we know our function y has to be some constant in the form of 1 plus a over 4. So plugging a 1 plus a over 4 back into our top equation, we get that on both sides. 1 plus a over 4, 1 plus a over 4. We cancel out our terms as much as possible. Oops, there we go. So then this becomes a simple quadratic polynomial. We can factor out things very easily. And we're left with 1, or a over 4 minus 1, quantity squared is 0. So that means a is 4. So that means that our mysterious function y is just 2. We're pretty sure that this was a typo up here, because otherwise that would be way too easy. Okay, so here is the second question that we're asked to solve. We're expected to solve some kind of dot product line integral, where we have a field function and our dr function. As vectors, we have these nasty equations right here for our field, and then our dr is just dxi plus dyj. We're told that it's along a path. X to the 2/3 plus y to the 2/3 is a to the 2/3, where a is some positive number. I think, if I remember this sketch correctly, it kind of looks like a star. Something like that, I think. Alright. So how do we solve this evil, nasty thing? I mean, if we're going along this line thing, we could probably, parameterize x and y in terms of function t, but yeah, how do we parameterize this thing nicely? Let's look for something else. Fortunately, if you remember your calculus at all, we have something called Stokes' theorem, which will help us tremendously. Basically, if we're given a line integral, f dot dr, that is equivalently the same as the area integral of the curl of the field, where, fortunately for our field in 2 dimensions, our curl basically becomes this condition, the j component of f derivative by x minus the f component, or the I component of f derivative by y. If you do all the nasty math, it turns out that all the terms cancel out perfectly, and you get 0. So that means that our integral, that our nasty line integral, just winds up being 0. Hooray! Okay, last easy, quote-unquote, easy question that I'm going to do today is we're asked to find a nicer formula for this series. We have the summation from n equals 2 to infinity of the sine of x to n power divided by n times n minus 1. So we're hoping to find this as some kind of function that satisfies all our points. I decided to just write the first couple terms of the series here, just to give you an idea on how chaotic this is going to be, because we have even and odd functions, and these things are just going to look really weird. So how are we supposed to find a way to combine them? So a little trick that we're going to use in this summation is we're going to take our n times n minus 1 product and break it up into 2 fractions. So we have 1 over minus n minus 1 minus 1 over n. And you can put these back together really quickly to check. So rewriting our first few terms of the series, we have sine squared times 1 minus 1/2 plus sine cubed times 1/2 minus 1/3 plus sine fourth times 1/3 minus 1/4. What I'm going to do now is I'm going to organize all of the coefficients together. So the 1 just goes with the sine squared. We have minus 1/2 sine squared plus 1 half sine cubed. So I'm going to group the sine squared over 2 together. We have a leftover term of 1 minus sine x. Likewise, I'm going to do the same with the 1/3. They both have a sine cubed in common. So again, we pull out another 1 minus sine x. And hopefully here you'll see a pattern where we will keep pulling out 1 minus sine x terms. Alright, so refactoring out our 1 minus sine x term from this side, we still have our sine squared on this side, and now we have this product, sine squared over 2 plus sine cubed over 3 plus sine to the 4th over 4, etc. So now you're thinking, what do we do with this? Again, this is just something you may or may not recall, but if you have a very small value, of absolute value less than 1, you can write its natural log, or negative natural log of 1 minus x, as this Taylor series here. We have x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4. Looks familiar, right? Yeah. Except we're missing this first term in front. So what we can do is, since our sine of x is between minus 1 and 1 for all our values, we'll have to come back a little bit and discuss when it's minus 1 and positive 1, but it's not really a big issue. Plugging in sine x for our formula, we have our summation right here. We have right here as negative log of 1 minus sine of x. And of course we're missing that first term, so we have to include an extra minus sine x. So, therefore refactoring out these terms, our sine squared term will cancel from up here. So what we're left with is just sine of x plus 1 minus sine of x times the natural log of 1 minus sine of x. Like I mentioned, technically we should pay special attention to when our sine of x function is 1, because what we have here, 1 minus sine of x, that would be log of 0, which is negative infinity technically, so that's not good. But two things to notice is that if we plug sine of x equals 1 directly into our original equation, we're going to have the summation of 1 over n times n minus 1. We're going to have a telescoping series where basically all the inside terms are going to cancel out, and you're going to have 1 minus 1 over infinity, which is 0, so we just have 1 left over. So the other thing we need to make sure is that our limit approaches that point of 1. So here we go, we have the limit as the sine of x goes to 1. Our same original function as before. I just did a quick substitution and called u sine of x. So we have natural log of 1 minus u over 1 minus u. I did this because, plugging in u, we're going to have negative infinity over infinity. That's not really going to help us at all. So let's use a L'Hopital's rule, where we take the derivative of the numerator and the denominator separately. We get 1 over u, actually this is negative 1 over u on the top, and then we have minus 1 over 1 minus u squared, and then we would gain another negative from our chain rule here. So we have negative 1 minus u, which of course as u goes to 1, this is simply 0. So all we have left is, so this whole product goes to 0 as our sine of x approaches 1, and we're just left with sine of x, which is 1. So our limit matches up, so we're totally fine on that part. So using just a really quick graph program, this is basically what our graph will end up looking like. Again, we have our continuity here at 1. There we go. Continuity at pi over 2, or sine of x is 1. And there is the same type of convergence here at 3 pi over 2. And of course, it's valid for all values of x, as this is a periodic function. So, alright, this is, hopefully I'll be able to do some more hard problems next time. This is Big Mac saying, better.